Qua guardi il valore, gli fai 11 centimetri, vai qua, c'hai 11,7, giusto? Quello che manca, lo vedi qua, e vedi qual è la tacca che si allinea per prima a uno di questi. Io direi che la tacca più allineata è questa, e quindi 2, quindi è 72, 11,72.
Anche la domanda è questo qua, e poi
Ok.
ci sta un pezzo che manca.
Sì, ma c'è sta pure qua.
No, ci sta
Buono. Sì, mi fa.
Ah.
Ok.
Oh, io queste cose purtroppo ne avevo mai fatte.
Va bene, hai fatto, ti manca il base dei coppotelli.
Ma adesso anche volevo fare queste cose.
Ah. Okay, just few minutes and we will start together. Okay, so let's go. Good afternoon, everybody. I will turn on the recording and I share my desktop. Okay, so at the moment we want to study this typical section stability, but using finite element and the lifting surface code. In particular, we will use a commercial code which will perform a structural, namely a dynamic analysis, so evaluating the mode and the frequency of the system. Next, in this code we will be perform an aerodynamic matrix, but including a lifting surface model, so no wake discretization. In particular, the lifting surface model is also known as DLM for doublet lattice method. Indeed, when you study the case of a very thin lifting surface, you see the integral formula for giving you the velocity potential or the downwash, you realize that the distribution of singularity is only reduced to a distribution of the phi on the n, what we called C coefficient or F coefficient on the wake, C coefficient. And so that coefficient, the phi on the n, are representing a doublet singularity on the surface. For this reason, in the case of lifting surface, we also have a method known as doublet lattice method, DLM. And this acronym is very used in the technical literature. So we have DLM, and together the aerodynamic matrix formulation plus the structural dynamic formulation will allow to solve our characteristic equation in terms of PK method as a very last numerical procedure of our code. However, we have to organize our input for the finite element code, and I will take this opportunity to show to all of you the input data file to be organized for this code. And for this reason, we have introduced this equivalent dimensional model where we have a center of mass, we have a center of elastic center here, and this black segment here is representing the wing, and we have a couple of two superimposed, initially superimposed node, which are the node 100 and 102, representing 100 the location of the airfoil, 102 the location of the fuselage, but this is actually a deformed configuration. In the undeformed configuration, the point 102 is superimposed with 100 with the 100 node as here. Okay, so this is our frame of reference, zeta and x. This frame of reference is, of course, a body frame of reference, which is fixed with the body in the undeformed configuration. And the body is actually represented by this lifting surface with unitary span length here. So the span is the y direction, and we have 1 meter in the span direction, and we have 2 meters in the x direction as airfoil chord here. Okay, our frame of reference is with the origin in the center of gravity, and we have translated our input undimensional parameter like CE and CG in the exercise number 2 with our dimensional parameter. Indeed, in this case, we have coordinates for the point, the center of gravity and the elastic center, which are center of gravity 0 abscissa and elastic center minus 0.2 meter, as you see here. Okay, and we have also determined our other parameter for our body. We have the mass with the mass entity. The mass entity is m. We can obtain this mass entity by this multiplication because we know the undimensional mass ratio like 3 here. And so we have mass per unit length equal to 11 kg.49. And again, we have also determined the moment of inertia with respect to the elastic center, J alpha, and the moment of inertia with respect to the center of gravity. This is equal to 2.4 kg/m² per meter. And the other one is higher, is equal to 2.78 kg/m² per meter. We have also evaluated the effective value of the spring. We have two-dimensional spring like KH, which is a spring in the vertical, and K alpha, which is a spring in the torsional sense. And for transforming our problem in a dimensional problem, we have fixed the length chord, the chord length is equal to 2 meters, but we have also fixed the omega alpha natural frequency as equal to 100 radians per second. And as a consequence, since we know the capital omega ratio frequency as equal to 0.8, we have here that omega h, which is capital omega by omega alpha, is equal to 18 radians per second per meter, of course. And therefore, we have a Springer stiffness KH as equal by this multiplication, and so we have 73,588 radians per second per meter and 28,745. Again, here we have as unit of measure, we have quantity like Newton meter by radiant, which is the measure of the stiffness, rotational stiffness. Okay, so we have our dimensional parameter, and this is the idea of our system in dimensional form. And now we have just to focus our attention on Nastran data input in terms of DBF file, and we will have also a description of this solver. This solver essentially determines the equation, the generalized aeroelastic equation, like the S square m plus k minus q es w equal to 0. So, and before determining this equation, we have to determine the mass and stiffness metrics in the original finite element coordinate, then perform a model analysis for determining the natural frequency and all the natural frequency together with the generalized mass and generalized stiffness, and then the real eigenvector. After that, the code is able to evaluate the aerodynamic metrics as evaluated in finite value of the reduced frequency. But I want to proceed step by step with you. And first of all, the Nastran input file structure. Which is a universal structure in terms of finite element code input. And this structure is subdivided in 3 parts. We have a first part. If you look at the manual, Nastran manual, I have the manual here, and this is the so-called quick reference manual in this Nastran version. You can download this manual as a student, and the first part is also known as executive control part and case control part, and finally the bulk data part. So we have executive control, we have case control, and bulk data. So we can distinguish this three part here as executive control part, we have the case control, and the third part is the so-called bulk data part, is the part number 3. Now, if you see this test file, we will see this in a few seconds. We have that this part is of order of 10 line maximum. The case control part is of the order of 10 line, and the bulk data is of the order of probably 1,000, maybe also million line, because in this bulk data part there is all the description of the model in terms of degree of freedom, grids, finite element, and so on. But in our case, the model is very, very simple, and therefore this part, we have a unique file. We have a unique file including all these three parts. And let's see together this file. I will share this file with you on the website, no problem. And this is the manual, and this is the file. Then the extension name of the file is maybe of two types. Typically, one have .dat for data, but also another standard extension for this file is bulk data file, so BDF file. So the extension, the typical extension is .dat or .bdf for bulk data file. Okay, so if you see here, I have used this amount of dollars characters as separator between one part and the other part. So the first part of the file is this, up to here. Okay, and this is the executive control part. In this part, one has the definition of the solver. So whenever you see dollars, you have a comment, and in this commented part, you have all the reference to this kind of model. This is a very standard model, and you see here this is the solution of PK flutter analysis method using analytical Tedorsen function. Indeed, in this special case, we will choose as option the Tedorsen aerodynamic as possible aerodynamic model, not the lifting surface panel method. But we can do this. We could use panel method, no problem. Okay. So solver 145 is the flutter solver. Is the solver able to give a numerical result for the aeroelastic equation? Reduce it in that form. Okay, this is the first part. In the second part here, we have in the so-called control case control part, we have the list of method we will use, or output to be used, or case in terms of case of force. But in the case of Flutter, you don't have case of force or boundary condition. Your problem is a free response problem. So typically, the word case imply in the part 2, the word case imply case of output that you can define, case of loads or boundary condition you want to perform, or case of methods you want to use for solving your problem. So case is used in a generalized form. In this case, I'm sorry for this, we typically specialize the method, and the way for specializing the decision in the input data file in Nastran is based on the system of label. Indeed, if you see this data input file, you see that, for example, method equal to 13, or f method equal to 3. So here we have just number, but this number is not essential. You could write here 17, for example, but if you write here 17, you are defining as a method for Flutter analysis picky method, in the sense that if you go to the bulk part here and you find the statement Flutter, okay, you have here 3, but now you have to write 17. Okay, and so that label are actually pointing this statement, and this statement you have this indication as PK, and this PK written here is indicating actually that we are using the PK method. Okay, however, as general rule, you have in the input Nastran input file a list of statement, and you have a statement per a line. Any line, for any line, you have a statement. You have a statement here, and so on. Okay, so we are here in the statement, in the case part, and in this case part, you are established that you will use in this solution sequence 145, you are actually deciding to perform your fractal analysis by using PK method, because in the Flutter statement down you have 17, and this 17 is linked to the 17 in the statement down. In the other case decision you have here are for the output, for example, and for example this CO means that you want to display, you want to be displayed any degree of freedom, and you want to print the eigenvector, all the eigenvector in your analysis, and so on. However, at this point, we need to be able to use the manual. How can we use the Nastran manual? This is the Nastran manual. This is the so-called quick reference, and quick means a file of, look here, quick means a document of 3,335 page, and this means quick. However, in this guide you have all the information for any kind of Nastran solver. In particular, if you go and you see here the part for the for the executive control. You have the part for the case control. And here you have the part for the bulk data. Now, please focus ourselves. For example, if you focus on control, executive control, you have the list of the statement which are characteristic of the executive control. And for example, you have an alphabetic sequence, A for alter, and this is just like a telephone book, up, CN, but for example, in our file, we have in the first part, in the executive part, we have Sol 145. For you have to find Sol, and therefore in Sol, S like so, you have E and alter. We have at the moment Sol. Okay, Sol. Sol specifies the solution sequence or main sub-D map to be executed. So here you are specifying your solver, and here you have a list of solver. Look, 101 C static, statics with options, static analysis, 103 normal mode analysis, and 145 aerodynamic flutter. And this is the solver we are using at the moment. Okay, and here we have an amount of about 15 solvers, typical solvers in structural and aeroelastic analysis. Okay, so go back to our file and go. So if you want detail, for example, on SBAC statement in the case control, you have to go to case control section. The case control section is this section, case control command. And in case control command, you have to find SBAC. This is the lucky day. I'm looking all statement with ST, the last character in the alphabet. So I have to scroll all the, oh my God. F, G, H, M, S, ST, S-stress, S-back, S-vector or S-back. Request the form and type of solution, set eigenvector output. So this is an option for having the eigenvector as output. If you write S-back or S-vector equal to all is an option. Displacement for all point mode will be output. Okay, and so on. If you write n, an integer number, n is the set identification of a previously appearing set command, and so on. Okay, But I want to focus our attention in the last part, the third part of our input file, which is the bulk part. In the bulk part, we have the model. We have to build the model, okay? And this part at the beginning is introduced by the statement begin bulk. Note that the space are important, are relevant, so you have to respect the space or not space, okay? And I want to list with you the relevant command we want to analyze in our discussion today, and we start with the grid statement. In the grid statement, we define the grid coordinate. And in particular, look, we have here 3 grid or 3 nodes. The node 101 to be defined, the node 102, and the node 100. The coordinates are easy to be defined. We have for the 100, we have, look, the axis, we have minus 0.2 meter, 0.5, and 0. Zeta is equal to 0. The same coordinate for 102, and here for 101 we have minus 0.2, okay, 1 meter, and zeta equal to 0. Okay. If you see the statement, if you see the data input file, you have here, look, we have minus 0.2, 0.5, and 0 for the grid 100. Okay, and for the grid 101, you have minus 0.2, 1, and 0. And for the grid 102, we have minus 0.2, 0.5, and 0. Okay, if you have some doubt about this sequence, you can see that you can look at the manual, go to the manual and go to the bulk data entry description. So we can consider this chapter 9 with all the bulk data entries. So you have an alphabetic facility here, and we want to see the grid statement. So the grid statement is just here from F to L, of course, because we have grid, and we can find grid here, grid is just here, and grid defines the location of a geometric grid point, the direction of its displacement, and its permanent single point constraint. So look, we have 1, 2, 3, 4, 5, 10 fields for writing our decision about the statement. In the first field, we have to write the grid statement. Then we have to define the ID, the identity label. Here, the CP is a label indicating the frame of reference. And then in the field 4, 5, and 6, we have to write the coordinate of the grid point, the X, Y, and Zeta. Again, here we have another frame of reference, but this frame of reference is potentially a different from frame of reference with respect to this here, because this first frame of reference is a frame of reference concerning the grid coordinate, whereas this here is a frame of reference concerning the displacement vector associated with the grid. So this is the distinction between the frame of reference for the X quantity, the coordinate of the node, and for the U quantity, which is the displacement and rotation of the node. So this could be different. However, if we do not indicate nothing, if you give no indication on this, you are deciding to assume the standard or default frame of reference, okay, which is the unique frame of reference of the analysis. And what about this PS or CID? The ID is the grid point identification number. CP is the identification number of a coordinate system. CD is the identification number of a coordinate system in which the displacement, constraint, or solution vector are defined. And PS is the permanent single point constraint associated to the grid point. What does it mean? It means the following. If you decide to constrain 1 degree of freedom of such a grid, for example, the first degree of freedom, yeah, you have just to indicate 1. 1 is for the first degree of freedom is constrained to be 0. In Nastran, there is a convention for the sequence of the grid of freedom, and in particular, there is a convention for 1, 2, 3, 4, 5, and 6. 1 is indicating the translation of the grid point, the first component of the translation, the second component of the translation, the third component of the translation, the first component of the rotation, the second component in the sense of X, Y, and Z axis, of course, the second component of the rotation, and the third component of the rotation. This is 1, 2, 3, 4, 5, and 6. So if you write 1, 2, means that you are constraining the first and second degree of freedom to be 0, and so on. Okay? So, practically, what happens? We have here that, for example, the grid 10, the grid 100, this is the name of the grid, which is located at this coordinate, minus 0.2, 0.5, and 0, as a constraint such that 1, 2, and 4 degree of freedom are 0. So this means the first degree of freedom, X direction, the second degree of freedom, Y direction, and the fourth degree of freedom, the rotation with respect to the Y-axis, because excuse me, the X-axis. So the roll, the rotation around the X-axis is 0. Okay. So, for example, no degree of freedom is for the grid 101, whereas the degree of freedom 102 is constrained at 1, 2, 4, 5, and 6. This means that only the third degree of freedom is free. In fact, the grid 102 here is actually representing this pure vertical translation, indicating the vertical translation of the fuselage. Okay? And so we have just described the 1, 2, 3 degree grid associated to our problem. Next, and this description is compliant with the draw I have here. Okay, as you can see. Now go ahead. After the degree of freedom, we another important issue is the format of this statement. As you can see here, I have a number of characters equal to 1, 2, 3, 4, 5, 6, 8 character. Excuse me. 1, 2, 3, 4, 5, 6, 8, 9. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have field of equal to 8 character, and you have to input your quantity inside this field. So when in the manual you see something like that, where is it? Where is it? Okay. When you see 1, 2, 3, 4, 5, and so on for indicating the field, you have to intend that in the first field with character from 1 to 8, you have to write a grid if you want to define a grid, in this case, a node for your problem. In the second field here, you from column or character 9 up to 16, you have to write the definition of your label for such a degree of freedom. So 100, 101 in our case, and so on. So in this case, we have skipped the definition of CPE, okay? And we have also skipped the definition of, excuse me, okay, CP, and here there are the definition of XY, X2, X3 in the field number 4, 5, and 6. Note that in our practical case, we don't have defined the CP, the frame of reference. In fact, we have a blank space here. Okay, so in the third field we have nothing, and therefore we are assuming that we are considering this default frame of reference, and so on. Okay, an alternative to this kind of format is the use of the comma. You can write an equivalent statement just writing grid, comma, 100, comma again, because here we don't have any statement in the field number 3, so comma again, and then minus 0.20, comma 0.5, comma 0.0, comma again, because we have another blank, and then 1, 2, 4. So this here is quite equivalent to the above. Okay. Okay. Next, definition of the elastic spring. Okay, and the elastic component, concentrated elastic component, are defined by this statement C_elas_2, which is for concentrated elastic element. So you are essentially defining a spring connecting two nodes. So the other statement is Silas grid, and we have Silas, which is the definition of spring element. So the message is that with the finite element code, you can define finite element as part of a material, part of a structure, but you also may define concentrated element, because you know very well that the final mathematical model for discretized structure or for a naturally discretized structure is quite the same. You always will reach a mathematical model composed by the mass matrix, the stiffness matrix, and so on. So you can also use the Nastran for concentrated parameter model, as we have just now here. So this elastic element is composed by, see the manual here, and looking for C_elas, the C is here, and we have C_elas2. Define C_elas2 scalar spring property and connection. Define a scalar spring element without reference to a property entry. So, and the syntax is the following. You have the name of this statement, you have an identification number, and in the third field here you have to define or write the stiffness of your scalar spring. And then G1 is the geometric grid point or scalar identification number. So you have to define your spring is connecting two grid, and then you have to write your grid here, the first grid, and here the degree of freedom of connection of such a spring. So, okay, so C1 is the component number, and G2 is the other node, and C2 is the other component number. If you have a damping coefficient, you may write this coefficient here and so on, but this is the elementary definition of our spring. So in this case, if you remember, yesterday we defined as elastic element, this spring with a KH equal to 1,000, so 11,049, excuse me, 73,488 radian per second. Okay, and so no, this is not radian per second. This is Newton per meter, and Newton per meter to the power 2. Better. However, the number is this. And going back to our data file here, we have to modify this number. Look, we are connecting we are defining, excuse me, the elastic element 103, and we are placing this spring from the degree of freedom 100 to the degree of freedom 102, involving the vertical tree, the vertical degree of freedom. So we are connecting the fuselage and the wing with our KH spring, and our KH spring is a quantity of about 73,588. Okay, and some decimals like that. For as concerning the rotational spring, we have this number, which is 28,745, which is the number we found yesterday. As concerned this, we don't know the decimal, and note the difference. Here we are connecting the degree of freedom 5. The degree of freedom, the grid 100, considering the rotational degree of freedom with the ground. Nothing, we have nothing here, because we are assuming that the rotational spring is at the moment creating a connection between the rotation of the section with the ground, not with another grid of the model, but with the ground. And so we don't have any other kind of node to connect the angular spring. Okay, so we have closed the description of the spring, and now another point is the point concerning the connection between our node 100 with the node 101. Here we are considering this double grid element connected by a rigid bar, because we need this two grid for modeling our wing, because we have to implement, we have to define an interpolation strategy between the structural and the aerodynamic degree of freedom. So the double definition of the node 101 and 102 is artificial. Excuse me, 101 and 100 is artificial. It's just to allow to implement a interpolation strategy between the structural degree of freedom, which are the degree of freedom of such nodes, and the aerodynamic degree of freedom, which are the aerodynamic degree of freedom associated with the unique lifting surface we are defining. Okay, so in a physical point of view, the definition of this stick, of this rigid stick, does not make sense, but is useful only for the numerics. Okay, and we have to connect 101 and 100 grid with the rigid bar, and this rigid bar connection is exactly given by this statement here, R bar. R bar is for rigid bar, so we are defining a rigid bar element. The name of the element is 101, and this rigid bar is connecting the grid 100 with the grid 101. And this rigid connection is such that the second node is a slave of the first one, in the sense that all the degrees of freedom are constrained. In order to better understand this, go to the manual. However, you have also the definition here. The rigid bar card defines a rigid bar. Okay, listed are the grid points at each end, and the dependent and the independent degree of freedom at each end. Okay, the number of independent degrees of freedom at the two ends must equal 6. Okay, so what does it mean? If you want, you can write, you can see the manual. In the manual we have R bar. R bar is here. R bar, define grid, a rigid bar with 6 degrees of freedom at each end. So you have a rigid bar like this pen here. You have 6 degrees of freedom here, and 6 degrees of freedom at the other tip of this pen, of this stick. And AED is the element identification number, and then you have GA and GB are the grid point identification. So in our case we have 100 and 101, and we have also CNA and CNB, which is the component number of independent degree of freedom in the global coordinate system for the element at grid point A and grid point B. So we have, in our practical case, so we are just showing how to define a rigid body straight or stick element by Nastran. So we have 100, 101, and so this field here, degree of freedom 1, 2, 3, 4, 5, and 6 are representing this CNA is representing the component numbers of independent degree of freedom in the tip A. So in the first tip A, this node, we have 6 degrees of freedom, and in the other tip we have no degree of freedom as independent. So the independent are the degree of freedom of the first grid you are defining. So in our case, the independent degree of freedom are the degree of freedom of the grid 100. And 101 are fully dependent on 100. Okay, so we have defined rigid bar connecting. So what this implies that, practically, this implies that the motion of this grid is identical to the motion of 100 grid. Is a slave of 100. Okay. Okay, so I will stop here. I want to continue my discussion for this model in the other hour. I hope this is useful for you. And I want to have a break now.
Professore, scusa.
Mm.
Senta, posso farle domande sulla seconda esercitazione?
Mi dica.
Sì, allora, la prima è che diciamo nel terzo punto, quando calcolo il root locus del sistema, mi vengono due rami, vabbè, che partono dai poli complessi coniugati, e quindi avrò che uno di questi attraversa l'asse immaginario, e quindi quello sarà il punto per cui ho il valore di U, diciamo, critico. E poi c'è un ramo che è tutto quanto sull'asse, diciamo, dei numeri reali, negativo, e che a un certo punto diventa poi positivo. Il valore per cui diventa positivo è il valore dell'autodivergenza, cioè
Secondo lei?
è quello, cioè sarebbe l'instabilità statica. Sì, scusi, statica.
Beh, perché? Perché
Ok,
altro potrebbe essere?
ok. E invece un'altra cosa, nel caso quello...
Potrebbe essere. Che altro potrebbe essere?
Sì, no, perché non... Sì, sì, effettivamente sì, no, perché inizialmente non mi tornava, poi...
Cioè, perché non ne tornava?
No, cioè, diciamo un ramo tutto sul...
Da dove viene? Da dove viene? Sarebbe essere una domanda
Io ho pensato...
interessante. Ascolti, se lei
Sì,
non ci avesse l'aerodinamica, ci avrebbe solamente due coppie complesse coniugate, no? Una per alfa, una per H e una per alfa,
sì.
giusto? Quindi avrebbe due coppie.
Sì.
Il
Quindi quelli
fatto
vengono dallo stato che abbiamo aggiunto noi, quello
quelli vengono
aerodinamico.
stati aerodinamici, certo. Il sistema non ha tanti poli quanto è il grado dell'ordine dell'equazione originaria, ma ce n'ha di più.
Mhm, ok, perfetto. E quindi diciamo quello stato aerodinamico che abbiamo aggiunto ci
Mm,
introduce anche questa stabilità statica, diciamo, la
sì.
divergenza. Perfetto. Invece un'altra domanda, nel caso di quando facciamo quello quasi stazionario,
Mm.
mi viene fuori un root locus che diciamo i poli complessi coniugati cioè, vengono stabili, quindi anche aumentando di molto la U tendono a un valore comunque stabile. Invece l'unica divergenza ce l'ho appunto su quelli statici, diciamo, sui poli reali. E io ho visto che tipo negli appunti c'era scritto che il fatto che facciamo l'ipotesi quasi statica, e quindi andando a porre C uguale a 1 e trascurando le derivate seconde, cioè fa aggiungere alle matrici di smorzamento un termine che viene dalla portanza, che sarebbe J omega, che moltiplica poi dei termini, e quindi cioè, è questo smorzamento aggiunto che fa sì che non ho instabilità a livello dinamico.
Il modello quasi statico è un modello che potrebbe essere usato anche nell'analisi dinamica, cioè nell'analisi di Flutter, ma uno a rigore dovrebbe utilizzare solamente quando nell'intorno della frequenza nulla, cioè nell'intorno perché se tu hai un andamento delle forze aerodinamiche che dipende da K quadro e dalla funzione di Thorsen, uno fa uno sviluppo di Taylor per piccoli valori di K, ci avrà solamente i termini JK e i K quadro non ce li mette, e che è quello che hai fatto. Giusto?
Ok.
Quindi quella sarebbe un'approssimazione che vale per basse frequenze, cioè per modi non troppo variabili. Il problema però è che viene, evidentemente, il tuo caso è un caso in cui il flutter non avviene per frequenze troppo basse e quindi ti dà risultati che non hanno molto a che fare con l'analisi esatta. Il problema è che questi modelli vengono utilizzati. Quindi questi modelli stazionari, quasi stazionari, sono approssimazioni di quelli completi, ma spesso non funzionano, come state vedendo, cioè non danno gli stessi risultati, per niente gli stessi risultati di quelli completi.
Quindi in pratica cioè, direbbe che non ho instabilità, però in realtà...
È lei che ha trovato, io lo sto
Sì, certo, io dai risultati sì, cioè, con questa ipotesi trovo che in realtà non ho flutter, ma quando in realtà ce l'ho, cioè nel senso per
sì,
questo che dico.
la città dovrebbe essere quello che lei trova con l'analisi non stazionaria, no?
Sì, sì, sì.
E quindi,
Va bene, perfetto, grazie.
prego.
Prof,
Sì.
e sempre diciamo riguardo quello che diceva il mio collega, infatti ecco stavo vedendo e per esempio plottando le F1 e F2 in funzione della frequenza ridotta, nel caso di aerodinamica statica io ottengo cioè, che la parte immaginaria tende indefinitivamente a zero per K molto grande, quindi significa che secondo questo modello io non ho possibilità di flutter, giusto?
La parte immaginaria tende a zero
Sì.
al crescere di
Per
non cambia mai segno la
K,
parte immaginaria? Mi
scusi?
stai dicendo che non cambia mai segno?
E guardi, le faccio vedere al volo lo
No.
schermo se me lo fa fare,
Sì,
Eh,
anche a me tendeva, diciamo, a zero senza mai cambiare
senza
segni.
mai raggiungere il
Sì,
flutter.
esatto.
partivate da zero tutte e due, però?
Sì, guardi, ecco, le condivido. E io praticamente ho aggiunto a ese.2, diciamo alla prima parte dell'esercitazione, ho semplicemente posto la funzione di Theodorsen unitaria e ho ricalcolato le radici.
Mhm.
E secondo questo modello ho che, aspetti, questo è F2, ok, che sia F1 che F2 praticamente non tendono mai, quindi, o meglio, scusi, la loro parte immaginaria tende indefinitivamente a zero, ma non...
Sei sicuro che lì non c'è nessuna attraversazione? Hai provato a zoomare lì intorno allo zero? Perché non lo so se tende a zero o ha scavalcato lì, eh? Non lo vedo bene. Non lo so. Domando, se l'hai fatto.
Allora, aspetti,
Poi basta vedere i file e vedere se sono numeri negativi quelli e sono numeri positivi.
sì, guardi, per esempio, ecco, a frequenza ridotta 3 viene praticamente 0,
Ok.
però comunque è 3 di frequenza ridotta.
E l'altro, quello a destra pure? A destra?
E quella a destra
Giusto?
e
A
abbiamo...
destra? Vediamo se è ancora positiva. Cioè devi vedere se c'è un attraversamento, no?
Sì, sì. No, tende a 0 in maniera indefinita, non c'è un attraversamento.
Ok.
Quindi
Quindi
secondo questo modello non ho possibilità di flutter, giusto?
sì, però vi faccio notare, per questo modello qua, non è che c'è bisogno che rifacciate il metodo tipo PK o tipo K,
Sì, ma
perché voi potete benissimo in questo caso fare un problema proprio di valori.
sì, sì, io infatti l'ho fatto in entrambi i modi. Aspetti, tolgo la condivisione.
Sì.
E cioè, praticamente l'ho risolto anche in maniera analitica, imponendo C uguale a 1 e P uguale a 0. E
Mhm.
infatti poi ho trovato proprio
C
l'espressione
uguale a
analitica che
0?
mi dà che
Scusa, C uguale a
la
1 che è T uguale a 0?
e P uguale a 0, ho
Ah,
detto.
P? Perché chi è P? Ma che cos'è per la
E
divergenza?
sì, ho imposto il polo a 0 e la funzione di Theodorsen unitaria. E secondo il modello analitico ho che la velocità di flutter, scusi,
Divergenza.
sì, di divergenza, sì, scusi, stavo facendo confusione. Secondo questo modello ho trovato velocità di divergenza 1,93 più o meno, e poi ecco stavo cercando di trovare la velocità di flutter nel modello quasi stazionario. E niente, ecco, quindi non ecco, diciamo che ho trovato che secondo il modello stazionario non arrivo al flutter.
Certo, potrebbe benissimo essere, certo che sì.
Va bene, grazie prof.
Bene?
Sì, grazie.
Prego. Okay, so let's complete our analysis in the data input, and now I want to share with you the presentation. Start the video. And okay, so we have just defined the stiffness, our stiffness. Now we have to place our mass in the vertical concentrated mass at node 100, and we have also to associate to this node a moment of inertia around with respect to the center of gravity or with respect to the elastic center. We have both of them, and so we can start our discussion with the so here we have the elastic part, the rigid bar, and now we have here the attribution of the mass by using this statement CMass2. CMass2 is a card which defines a scalar mass element without reference to a property card. It lists the mass, degree the number, and its degree of freedom component. When two degree, okay, so we are representing the fuselage mass, and so the statement is such that in C mass 2 we have in C mass 2 C here C mass 2 define a scalar mass element without reference to a property card. So in C mass 2 we have the unique identification number, we have in the third field the value of the scalar mass, and then in G1, C1 we have the geometric grid or scalar point identification number. And C1 is the component number, because when you put a mass in a degree of freedom in a grid, you have to decide to which degree of freedom this mass is associated to. Okay, and so in our case here we have simply the following. In 100, this is the mass element identification label, and in the third field you have here the value of the mass in kilogram. Note that, as Mr. Linari suggested to all of us, typically we are using always quantity in the same system of measurements. Therefore, this number, this huge number, which is 9,999,999, is the amount of mass associated to the grid point 1, 2 in the zeta direction. So we are talking about the fuselage mass, okay? And we are giving to this fuselage mass a very huge mass. So huge that this mass keeps to be fixed with respect to the rest of the aircraft. So if we put a huge mass there, we are practically assuming that the springs are constrained to the ground, essentially, and to the airfoil. So we have a huge mass at the moment. So in the case you are requested to consider the fuselage effect, you have just to reduce this number from this value to a current value as assigned in the exercise assignment. Okay, so this mass 2 is the assignment for the mass for the fuselage mass. Remember that the fuselage mass is just translating, but the airfoil mass is not purely translating. The airfoil mass is translating and is pitching around the center of mass. So we need to a more sophisticated definition for the mass distribution in the case of the wing, and therefore we use another statement. We use the statement CONM2, concentrated mass statement number 2, and by this statement here we can define a moment of inertia tensor in a generalized way, not only the mass but only the moment of inertia. Okay, as in the following. Look for CONM2. CONM2 is here. Excuse me, the manual. CONM2. CONM2 is in the other chapter here. CONM2. Okay. Define concentrated mass at the grid point, and here you have identification number, the grid point identification number, a frame of reference, which is the standard. We have M, the value of the mass value, and we have these three coordinate points, x1, x2, x3. x1, x2, x3 are offset distances from the grid point to the center of gravity of the mass in the coordinate system defined in the field 4. So in the field 4 you are defining coordinate system, and in such a coordinate system you are defining the offset, so the distance between the mass location and the grid point. If in this field 4 you write -1, in which case x1, x2, x3 are the coordinate not offset of the center of gravity of the mass in the classic coordinate system. So if you write here -1, look, this is the case, we use -1, this quantity are indicating the coordinates, not the offset, of the center of gravity of the mass in the basic coordinate system. So in our cases, we have that the location, we have the center of mass here, and this location is in the point x equal to 0, y is equal to 0.5, and zeta is equal to 0. This is the location of the center of mass. And therefore, here we have 0, 0.5, and 0. Okay, look that this 0 point is 0 because we are within the field here, just here, look. Okay, so this is the value of the mass in kilogram, 11.49822 kilogram. We evaluate this value yesterday, remember? Yesterday. M equal to 11 kilogram, 0.49 here. Okay, so we have write this here, and so the rest of the statement, in the second line we have Ij is mass moment of inertia at the mass center of gravity in the coordinate system defined by field 4. So here we have to write all the components of the moment of inertia. 1, 1, 2, 1, 2, 2, 3, 1, 3, 2, and 3, 3. So all the component of the tensor, but the only component we have is the component with respect to the y-axis, because we have the y-axis is the principal axis moment, and the moment of inertia we have to indicate is only the moment of inertia I22, and this I22 is the principal, is this jg, which is equal to 2.414 kilogram by square meter per meter. And this number is just represented, has to be represented at the location 4, I22, and all the other are 0. Indeed, look, we have 0 everywhere, 0 here, and look, here we have a comment line just to remind that I have to write I11, I21, I22 in this field. And in the I22 field, I write 2.414628. Okay, so okay, the moment of inertia is fixed. Okay, next, no damping, so we don't care about damping, and we have to prepare our aerodynamic model. The structural model is concluded. Aerodynamic, we have to define this. We have to define this lifting surface. Our airfoil starts here in the coordinate, look, minus 0.8 meter, because this is the origin. And therefore the leading gauge line is at x equal to minus 0.8 meter, and the trailing gauge is at 1.2 meter. Okay, so in the first statement here, we have to indicate aero card. Look at this card, aero, and we have in aero case control. No, case control. Fuck that. A for aero. Okay, give basic aerodynamic parameter for unsteady aerodynamics. So these basic parameters are AC SID. AC SID is the aerodynamic coordinate system identification. We can use the same reference system as the structure, so we can leave 0 in this second field here. Okay. Next, 3, velocity. Here to indicate the velocity, force for aerodynamic force data recovery, and to calculate BOV parameter. We don't care about this velocity here, because this velocity is the flight velocity in the case you have to evaluate a response problem. You are flying and you want to calculate the load and the aerodynamic in a assigned velocity, but this is not the case. We don't care of this velocity here, because this velocity value is referred to a special case of aerodynamic flight condition. But we are performing a factor analysis, so this velocity is not a fixed value, but it is varying parameter for our locus, for example. Okay, next. Other parameter, this is important, reference chord. Reference chord. Why the reference chord is important? Because the reduced frequency is defined with respect to reference chord. Easy. So we have to fix this reference value, and our reference value is 2 because in NASA it's assumed that the reference length is half chord. Okay, and in fact this point, okay, so we indicated in our data here 2 because reference chord is 2 in our case, 2 meters. 0.8 plus 1.2 is 2. Okay. Go ahead. We have also rho ref. Rho ref is the density value of reference, and so we have indicated 1.22 for air density, 1.22 in this field here, and this field are for assumed symmetry with respect to XZ axis or XY axis, but we don't indicate any kind of symmetry for our problem. Okay, so arrow is okay. It's okay. Now let me skip this spline statement at the moment, just a second, this spline statement and this set statement, but I want to consider this C aero 4. Okay, C aero, any kind of C aero statement are card defining the type of unsteady aerodynamic to be used. For example, C aero in the we have C aero. You have C aero 1, 2, 3, 4. So we have 4, for example. Define an aerodynamic macro element for strip theory. What does it mean? I don't know. And C aero 3. Define aerodynamic age of Mach box lifting surface. C aero 2. Define aerodynamic slender body interface. C aero 1. Define aerodynamic macro element panel in terms of 2 leading edge location and set control. This is used for double lattice theory for subsonic zona. Too complicated. 3, 4, 5. In other words, you have essentially in C aero 4 you are currently using the Tudorsian theory. You are imagine to subdivide your wing in strip, take the wings and divide the wing in strip and apply your Tudorsian section for such a strip. And this is the case we want to use now because we want to compare our result with the analytical result. And so Nastran will use the same aerodynamic we have used in your exercise number 2. Okay? And this is the strip theory. Why strip theory? Because in the strip theory concept, we don't want to use a three-dimensional aerodynamic, but we want to imagine your wing as divided in strip, and you want to apply for each strip the two-dimensional theory of Theodorson. Okay, and this is the theory we are using. If you want to use a more general theory, you have to use not the option CI04, but you have to use the another option for you. And this is the option we will use in the last exercise number 4. I will assign to you. Okay. Okay. So, but at the moment we want to compare our result with the result we have obtained in the exercise number 2. And so what about CI04? In CI04, we are currently defining our gray surface like this, and we have essentially to fix the position of this lifting surface with respect to your structural parameter. So in this case, you are able to move your lifting surface with the Dorsen theory forward or backward with respect to the structural location. And that's all. And after this process, you have to decide how to correlate your aerodynamic degree of freedom with your structural degree of freedom. In fact, I want to focus on this point. I want to focus this point. I want to focus this point here. We have also, excuse me. Okay. We have defined also C mass. We have defined the other mass definition, aero, and now we have C aero 4. Okay, we have a structure. And we, as output of this structure, we have the displacement in the degree of freedom 100, 101. So the finite element degree of freedom. And at this level, we want to consider an input for the aerodynamic. But as input of your aerodynamic, in order to build your aerodynamic matrix E, you need to represent your modal displacement in the aerodynamic system of frame of reference. So you need to represent, remember, in the E1 definition, you need the displacement of mode shape, but you need displacement in the aerodynamic frame of reference. In the output here, you will give the pressure and the generalized force in the aerodynamic frame of reference, and yet you have to modify this in the structural frame of reference. And then you need to decide a strategy transforming this quantity from the aerodynamic frame of reference to the structural frame of reference in both sense, in this sense, but also in this sense. In other words, you have, for example, a displacement in this aerodynamic, in this structural frame of reference, in this structural point. You have the displacement in this other structural point. You have a displacement here, you have a displacement here, but unfortunately, your aerodynamic control point is here. And then you have to assume an interpolation between the structural displacement, and you have to determine this displacement in the aerodynamic grid. And the way for performing this is the spline interpolation system. Spline is a special kind of interpolation given by polynomial of third order. When you have a beam, you know a beam in 2 points, and you know in the 2 point the beam value and the excuse me, let me do an example, a practical example. This is a beam. Can you see this beam? You have a value of the displacement in this point and a value of the displacement in this point, but you have also a rotation in this point. Okay? If you determine this beam displacement value, once you assign the rotation, the displacement here and here, you have a spline, cubic spline, which is a cubic. This cubic is exactly the value of the displacement given by this beam. This is a metallic beam, okay? Like that. And the spline is a system used in Nastran for interpolating the structural value of the displacement into the aerodynamic control point. And this is useful, for example, for mode shape. If you have the mode shape in the structural mesh and you need to know the value of the mode shape into aerodynamic mesh, you may use this kind of interpolation system. And this interpolation system is defined just here by this two statement. These two statements here, spline 2. Okay, so we are ready for talking about spline 2, set, and CIRO4. Okay, CIRO4 is defining your surface. Your lifting surface, the name of your lifting surface is 1000. This is the name of our lifting surface. We have just a Theodorsen rigid lifting surface theory, and the property of this surface is 1000 again. This 1000 is a dummy quantity. Okay, after that you have L span. L span is the number of strips you have in span direction. We have only one element. Okay, this plus CA1 is a continuation statement to continue your statement in this other line here. So you have a CA1 here and you have a CA1 here. Okay, next, finally, you have just to define for complete your card, you have to define if this is your control surface, you have to define the coordinate of this node 1, the length between the node 1 and node 2, chord 1, 2, and you have to define the node 4 here, the coordinate, and the length between the node 4 and the node 3, chord 4, 3. This is the definition of our flat lifting surface. And we can define this just here. Look, in the statement, we have x, y, zeta value for minus 0.1, 0, and 0, which is the coordinate of the point 1, x1, y1, and zeta1. And this x12 is the chord length between the node, the leading gauge and the trailing gauge node. So 2. This is the length of the lifting surface. Then we have the point number 4 in the lifting surface, and this point number 4 is located for x equal to minus 0.8 x value, 1 is the y value, and 0 is the zeta value. So we are talking about this point here. We are talking about this point here, chord 1, 1, 2, and we're talking about this point here with coordinate minus 0.8, 1 y direction, and 0 for the direction. So for assign this gray surface, we have to assign the coordinate of this point, this length, this point, this length, and that's all. Here. Okay. In the spline definition, we have just to assign which are the structural nodes to be splined in which kind of lifting surface. In fact, if you take spline 2, spline 2, define a beam, oh wow, we have understood what beam spline for interpolating motion and force for aeroelastic problem and on aerodynamic geometries defined by regular arrays of aerodynamic points. So we have to include in this statement the idea of the spline, C-aero is the aero panel or body aero. In our case is our 1000, which is identifying the aerodynamic surface. ID1 and ID2 are the first and the last box in the body element. Well, but we have only one box because we have only one panel element. If we have many panel elements, we could indicate the first and the last panel element in our interpolation strategy. So this indication is on the aerodynamic, and this other indication, set G, is on the, not on the aerodynamic, but on the structural set of nodes to be interpolated. In fact, set G is the set 1 defined and composed by only the structural node 100 and 101. So we are defining a spline. The number of the name of the spline is 1201. This spline is between the lifting element 1000, defined here as 1000, with panels from number 1000 to number 1000. So we have a multi-flavor ice cream with only one flavor, chocolate, only one panel. And then we have a set, structural set, the structural set named 100 and 1100, which is this here. Okay, so we are interpolating this set of structural node, finally we have found the node of the rigid bar from 1. This is the motivation of using rigid bar, because for interpolating the structure node, we need almost 2 grids. That's the reason of the using of rigid bar from 100 and 101. Okay, so we are interpolating the aerodynamic point included in this aerodynamic surface 1000 with the structural point included in 100 and 101. Excuse me. Okay. These other parameters are parameters regulating the flexibility of the spline for interpolating, but these are default value. Okay. The last but not the least are some parameters for defining the aerodynamic matrix calculation. And this is the final point. In fact, later here we have this P property aero 4 is a dummy card, like to 1000, like this 1000 here. But this card is very interesting because in this card you could choose to use a finite state aerodynamic or not for evaluating your Tedorsen function. In fact, if you go to this P aero 4, look, we have the default value here, but if you go to P aero 4 in the manual, P aero 4, in P aero 4, define property of each strip element for strip theory. Look, you can define here complicated quantity. Look, you know probably this in your life, huh? Or not? So you could define number. What is the exponential coefficient used to approximate CK? Why exponential coefficient? And this coefficient are this B, beta. Look. Why exponential? Because the people who wrote Nastran was ignorant people in general. In the average, these people are not so smart. But the Tedorsen function is a function defined in Fourier domain. And so the approximation is in terms of zero poles. When you inverse transform a fractional structure in frequency domain, you have an exponential one. So talking about exponential coefficient is the same way to talking about poles in your structure. Okay, and so the message is that you can select here if you want an approximation of the Tedorsen function in terms of number of poles necessary for approximate this. Okay, and that's it. We don't use this approximated function. In fact, if you leave the default all 0 here, 0 is the pure Tedorsen function with any kind of approximation. So this flag 0 means use the Tedorsen function. You can, if you want, use alternate value like 1, 2, 3 for approximate with 1, 2, or 3 poles for your Tedorsen function. Okay. Okay, this is P aero 4 for you. And now. Okay, what is this? This is the following. Now we are using the aerodynamic matrix, and we can select this aerodynamics matrix is generally function of the reduced frequency, but as we will see later, is also function of the Mach number. So if you have a couple of this value, you have a value for the aerodynamic matrix. So this is fixed to be 0 in our case, but we can decide where evaluate our aerodynamic matrix for a fixed set of value for K1, K0, K1, K2, K3, K4, and these are the reduced frequency value for evaluating your aerodynamic metrics. If you need an intermediate value, the code will interpolate this value during the PK process. Okay, so go back here. We have decided here to evaluate MK area means Mach and reduced frequency value for the aerodynamic metrics evaluation. So you have 0 for Mach number, but you want to evaluate the reduced frequency in 0.001K, 0.04, 0.08, 0.03, and so on. Okay, all these are evaluation of the reduced frequency up to a maximum value of 2. Okay, so this are the value we decide to evaluate the aerodynamic metrics. Period. Last assignment is the following. Here, how many modes to calculate for our analysis? We have how many degrees of freedom? We have the vertical displacement and the displacement of the mass. So we have a maximum degree of freedom in this case about 5. So we are asking for a number of structural mode which is greater than the number of the degree of freedom. So we are asking for the maximum number of structural mode evaluation. Okay, but this is the evaluation. This is the use. We are asking to use 3 Lagrangian modal variable. You could ask for evaluating a number of mode higher with respect to the number of generalized variable you are using. You could ask for evaluating 8 mode of vibration, but you could ask to use a 3x3 modal system for evaluating the flutter. These two requests are independent. As you can see here, you have 8 here and 3 here. And finally, the last statement is flutter. Flutter is a statement for asking the kind of analysis. You are asking for a PK analysis with parameter defined in the statement 1, FL factor 1, 2, 1 for the density, 2 for the Mach number, and 3 for the velocity. So these 1, 2, 3 are here, and here you have the range for your root locus. So actually, for your root locus, we said many times, many times that the parameter are 3. The parameter for the root locus are density, I'm finished. Density, Mach number, not relevant now, and U infinite. So we are fixed at the moment 1 for density ratio. This 1 means that you are considering a density such that the ratio between the density you are considering at the reference value of the density. The reference value was defined here by you by this arrow. This is the reference rho reference 1.2. So you are considering the sea level value for the air density. You are not considering the Mach number, 0 value for Mach number, and you are considering a velocity between 16 meters per second up to 200 meters per second. So you are asking for a 1950 evaluation of the velocity for your root locus from 16 to 200 meters per second. And that's it. Now we launch the analysis and see what happens. We launch Nastran. We have to trig this input file, our input file we have illustrated up to now, and then run. Okay. Okay, finished. The analysis is completed, and we have to see the output file F06 file. Okay, so this is the result, blah, blah, blah. The comments are also reprinted in the output file. So we have again our, this is an option to reprint what we have input in the file. No error, no error. So this is the summary of the model. We have one lifting surface, one card arrow, one C04 lifting surface. We have two elastic element. We have one statement for CMAS, one statement, blah, blah, blah. Okay. We have 16 MCairo1 card and all the other. Okay. This is the summary of your statement used. And first of all, you have your structural modal analysis. This is your modal analysis. You have three modes. You asked for three Lagrangian variable, three mode. And the first mode frequency is 0. This is the frequency in Hertz. So 0 Hertz. This is 0 for engineering. And we have 11 Hertz and 18 Hertz. For why 0 Hertz? Because our system is this, remember? And in this system, we have a rigid body motion. So this is the first mode of vibration. Next, you have other mode of vibration. Firstly, we have a mode of vibration in 11 Hertz and in 18 Hertz. The corresponding eigenvector is the eigenvector number 1, 2, and 3. The number 1 eigenvector gives to you a translation equal to 1 for the grid point 100 and 102, and rotation at 0 rotation for the grid 101. So we have a translation of your model, a pure translation. But in the eigenvector, for the eigenvector number 2 and 3, you have a motion for the grid of freedom 100 as 1, and you have 0 for the degree of freedom number 2. So we have the fuselage fixed, and you have the wing translating with respect to the fuselage with 1, and almost 0 rotation of the airfoil. So the airfoil is actually moving. This is the fuselage. The wing is moving up and a bit rotating. So the mode is just like this. It's mainly bending with a bit of torsion, like that. The last mode has a rotation, a significant rotation, but a very small. So the last mode is mainly pitching, and you have a bit of translation. So you have something like that. The coupling between bending and torsion is due to the fact that you have the center of mass and the elastic center separated. And finally, go to the flutter analysis. I want to go to the flutter analysis. Remember, let me 1 minute for displaying the result. Remember that we have here decided to scale our model. Multiplying this by 100, and therefore our speed, you have a speed which is equal to, remember this, we have that undimensional velocity is equal to the dimensional one, remember, by omega alpha divided by b. Okay, is this true? Or no, it is b divided by omega alpha, sorry. Okay, so we have that the dimensional velocity is equal to undimensional 1 by omega alpha, which is 100, and divided by b, which is 1. Okay, so we will see some result. If you have already obtained result in your exercise number 2, you have just to multiply your result by 100 to compare your result in exercise number 2 with the present result. Okay, so drum and look, and you have to see the so-called flutter summary at the end here. Skip this part and go here to the flutter summary. Okay, this is the flutter summary table. The flutter summary table is the following. You have the velocity in this column. You have the point. Point is the root. Excuse me, is the pulse we are following. This is the velocity. 60 and something else. This is the root locus parameter, the velocity. And here you have damping and frequency. In other words, you have the complex eigenvalue, real part and imaginary part, or damping, which is the imaginary part divided by the real part by the imaginary part, or the frequency. Okay. A fast way is to see the damping. So look, this you have stable quantity here. You have a minus. So go ahead up to a change of sign to this -1. So -1. Okay. Stable. Of course, you can take this couple of points and plot on your draw for a root locus by Nastran. You can do this. Cat this table and perform a root locus. Minus. You have many points. You have many points. Minus. Oh, we have a change of sign here. The damping is from negative value to positive value, and the velocity is 193 in dimensional meter per second. Undimensional is 1.93. Is this sound something to you or not? This is a divergence. Why divergence? Because here you have correspondingly zero frequency, practically zero frequency. Look to the complex eigenvalue. You have an eigenvalue something 0. Okay. So you have a divergence value for this model, for this velocity, and go ahead because we have other poles to be checked. Negative. Oh! Change of sign here. We have a change of sign in the real part, and you have an imaginary part not equal to 0. So this is a flutter, and your flutter velocity is from 118 to 119 meters per second. Stop. I finished. Are you happy to see this or not? I finished my lesson. Now it's up to you. Okay? So, at the end of the story, we have found for divergence a flutter, for divergence a velocity of about 192, and as a flutter we have found 100, almost 120 meters per second. Okay? And probably this should be in agreement with the result obtained in exercise number 2. Okay? So, we have a commercial code which is able to reproduce your simplified model, but the identical commercial code can be applied to an actual wing or an actual aircraft as well. Okay? Bye-bye. I will share with you this file as usual in your common depository in Teams. Okay?
Scusi professore.
Sì.
Potrei fare una domanda che non relativa al corso, quindi
Ok.
se qualcuno ha delle domande sul corso le faccia pure, cioè gli do la precedenza, ma se non c'è nessuno volevo chiederle una cosa.
Sì.
Io e un altro studente che dovrebbe essere presente, Alfonso.
Sì, salve.
Ecco.